All right, so welcome back. We're going to be looking today at a problem that is a conservation of momentum with a collision in multiple directions. So here it says we have an object with mass m1 with an initial velocity of 20 meters per second to the right. It's going to undergo an off-center collision with a second object of mass m2. So here we don't know m1 or m2, and they are different. The second object is initially at rest. After the collision, the first object is moving 15 meters per second at an angle of 25 degrees to the original motion. After the collision, we're looking for the direction of the second object. So let's go ahead and draw a diagram to see what we have going on here. So we have our first object, and let's just have it going to the right at 20 meters per second. It's going to undergo, I guess before we get there, let's go ahead and show the other guy. The other guy is sitting here, so its initial velocity is 0, and this would be m2. So this would be the before. After the collision, it says that the red one, the initial one, is going to go up at an angle of 25 degrees, and it has a final velocity of 15 meters per second. We know just from seeing collisions that the momentum has to cancel, and so we can go ahead and make the assumption that the blue guy is going to go down at this angle. And so this is what we're going to be solving for here, is what is the direction. So because momentum is a vector, and we have multiple directions here, this means we're going to need to set up a conservation of momentum for both the x component and the y component. So we can start with the x component because that's the original direction that we're in. So m1 v1 plus m2 v1, and I guess we can even call those, this would be the initial for both of these. We're going to just color code here to make sure we know which ones are different. So those are our initial setups, would then have to be equal to, in the end, they're going. So if we're doing the x component here, we're going to be looking at the cosine. So it would be m1 v2 cosine of its theta plus m2 its final velocity and the cosine of its angle. Well, we know that originally this guy isn't moving, so we can actually cancel that one out. We can move some things around, and what we end up getting is m1 v1 minus m1 v2 cosine of theta is going to be equal to m2 v2 cosine theta. I do want to note, and I'm going to go ahead and plug in 25 for that first theta. I also, once again, want to note that this V2 and this V2 are different. Instead of giving them another subscript, I know they're different because I'm using different colors here. So this is talking about the velocity of the second disk, and this one's talking about the velocity of the first disk. So here what we've done is we've dealt with the momentum in the x direction and set up a conservation of momentum problem there. But we also know that there's a total conservation of momentum. So not just in the x direction, but also in the y direction. So we're going to do a similar statement, but for the y direction. Well, when we start, there is no y movement. So we know that it's going to be set equal to 0. The initial is 0 because there's no y movement there. The final then would be m1 v2 sine. I'm going to go ahead and put in 25 because we know that it's 25. If we look at the blue disk, it's going to be m2 v2 and then its sine. So now we have two formulas. Well, when we look at this, there are a lot of unknowns. Yes, we know 25, we know the velocities of the red disk, the before and after, but we don't know the masses of either disk, nor do we know the velocity of the second disk after. So we need to come up with a way to solve this that is going to involve canceling out a lot of variables. The other thing that I noticed is that I'm dealing with sine and cosine, and I know that sine divided by cosine is going to give me tangent. So what we can really do is divide these two. It's not a process that we see a lot, but it is a process in solving a system of equations, is to divide your two equations. Before I do that, notice that my x1 has all of my reds on one side, my blue on the other. I'm going to do the same thing here because it's set equal to 0. I'm going to change this into my equal sign. That also means that I subtracted this over, so now I have a negative. So to get the cancel, once again, I want sine to go on top because I know it's sine over cosine gives me tangent. So I'm going to take my py and I'm going to divide it by my px. So now if we look carefully at this, we hope that it canceled out the variables we didn't know. Well, on the red side, I have an m1 in each term, so I'm going to get rid of that. On the blue side, I have m2 and v2 in each term. Simplifying this expression is going to give me negative v2 sine of 25 over v1 minus v2 cosine of 25. And that is set equal to the tangent of theta. Well, now we know our final velocities for the red one. It started with 20 and it ended with 15, so we can plug those in. We have our thetas for the red one in, which means our only unknown is therefore the blue theta, so we're good to go ahead and solve this out. So we go ahead and plug in these numbers. Negative 15, because this is our final velocity, sine of 25 over 20 minus 15 cosine of 25. We know that if we really wanted to, we could say this is the inverse tangent of this number. And that will give us our theta out. So we're going to put this in our calculator. Please be very careful. Make sure that you are typing things incorrectly using your parentheses where you need to. And make sure you're in degrees here. So you should get approximately that the inverse tangent is going to be negative 9.89. The number keeps going before you can round. So we're going to take the inverse tangent of that number. And we get a theta of negative 44.7 degrees. Before we're finally done, we need to actually come back to our problem and say, does that make sense? So if we look at our diagram, we see that because the red disk went up, in order to cancel out, we know that the blue disk is going to have to go down. So having a negative angle here in the first quadrant, or I guess the fourth quadrant, is going to make sense. So double checking that and always making sure that it makes sense in the content of your problem. So just going back and looking at this one overall, at first it seemed kind of scary because we didn't have that much information, but we started where you should start with any conservation momentum problem, especially in two dimensions, just like a good forces problem. We did a conservation on both sides. So we did a conservation in the x and a conservation in the y. Then from there, it was just trying to figure out the best way to solve it. Once again, I ended up dividing the two because I knew that I had a lot of unknowns and I wanted to see if I could get them to cancel. Also, whenever I see that I have sine and cosine, if we divide, we can turn that into tangent and we can go from there. And there you guys have it. This is your problem for conservation of momentum in multiple directions.